In the spring of 1943, somewhere in the dust-choked valleys of Tunisia, a peculiar drama was unfolding. The North African campaign was entering its final, brutal phase. German and Italian forces, trapped against the Mediterranean coast, were fighting a desperate rearguard action. Every day brought fresh disasters. Every night brought the rumble of Allied armor closing in. And on one particular morning, beneath the pale African sun, a single American tank would begin a journey that would shake the foundations of German military engineering. The tank was an M4 Sherman, medium weight, reliable engine, standard armament. Nothing exceptional by American standards, but to the German forces scrambling to hold their collapsing perimeter, it represented something far more dangerous than firepower. It represented a production miracle they could barely comprehend. This particular Sherman had been disabled during a skirmish near the ancient ruins of Carthage. A lucky shot from a concealed anti-tank gun had damaged its tracks and killed its crew. When German recovery teams arrived, they found the machine largely intact, operational even, once the tracks were repaired. They also found something else. Painted on the turret, in crude white letters, were the words, "War Daddy 2." No one knows who christened that tank or what happened to the original War Daddy. Perhaps it was lost in Sicily. Perhaps it never existed. But the name stuck. And as that Sherman was loaded onto a transport ship bound for Europe, as it crossed the Mediterranean under guard, as it rolled through occupied France and into the heart of the Third Reich, that name became a legend among the German engineers who would soon take it apart piece by piece. The story of War Daddy 2 is not just the story of a tank. It is the story of two fundamentally different approaches to war, to industry, to the very nature of engineering itself. On one side stood Germany, a nation that prided itself on precision, on craftsmanship, on the relentless pursuit of technical perfection. On the other stood America, a country that had learned to think in terms of scale, of speed, of good enough being infinitely better than perfect if you could build 10 times as many. And when these two philosophies met in the laboratories and proving grounds of Germany, the collision would send shockwaves through an entire generation of engineers. But to understand why War Daddy 2 mattered, we must first understand the world it entered. By 1943, German tank design had reached a kind of technical zenith. The Panther, the Tiger, these were not mere vehicles. They were manifestations of a particular engineering religion. Every component was machined to microscopic tolerances. Every system was designed to maximize performance. The Tiger's 88mm gun could punch through nearly any Allied tank at ranges exceeding a mile. Its frontal armor was virtually impenetrable. In a one-on-one duel, a Tiger was unbeatable. And German engineers knew it. They had created the finest fighting vehicle on Earth. But there was a problem. Actually, there were many problems. A Tiger tank required over 300,000 man-hours to build. Its interleaved road wheel system, designed for superior weight distribution, meant that changing a single damaged wheel could take an entire day. Its Maybach engine, a masterpiece of precision engineering, demanded constant maintenance and broke down frequently in the harsh conditions of the Eastern Front. And worst of all, Germany could only produce about 1,000 Tigers during the entire war. Contrast this with American Sherman production. 50,000 units. 50,000 tanks rolling off assembly lines in Detroit, in Gary, and Pittsburgh. Tanks that could be repaired by any mechanic with basic tools. Tanks that could run on almost any fuel. Tanks that, yes, were inferior in direct combat, but that could be everywhere at once. The German High Command knew they had a problem. But knowing and understanding are different things. Throughout 1942 and early 1943, intelligence reports had been streaming in about American industrial capacity. The numbers seemed impossible, fantastical. American factories were producing a new bomber every hour, a new tank every 30 minutes. Surely this was propaganda. Surely no nation could actually achieve such production rates. The Germans had their own factories, their own assembly lines. They understood manufacturing, and they knew that quality took time. This was the mindset that War Daddy 2 encountered when it arrived at Kummersdorf proving grounds south of Berlin. Kummersdorf was Germany's primary weapons testing facility. Hidden among pine forests, protected by layers of security, it was where the Wehrmacht evaluated captured enemy equipment. Soviet tanks had been tested there, British tanks, French tanks. Each one had been methodically examined, fired, driven to destruction. The engineers at Kummersdorf were among the finest in Germany. They had designed components for the Tiger. They had consulted on the Panther's development. They knew tanks the way a surgeon knows anatomy. And they were absolutely convinced that the Sherman would be a crude, hastily built machine that would fall apart under serious examination. The initial inspection seemed to confirm their prejudices. The armor was welded, not interlocked. The transmission was a simple synchromesh design. The engine was a modified aircraft radial, mass-produced and unsophisticated. The interior was spacious but utilitarian. Everything about it screamed mass production. Everything about it violated the principles of German engineering excellence. Then they started testing it. The first trials were basic. Drive the tank around the test track, evaluate its handling, measure its speed. The Sherman performed adequately, nothing impressive, exactly what they expected from a medium tank. But then they started pushing it. They ran it for hours without maintenance. They drove it through mud, through sand, through conditions that would have crippled a Tiger. They deliberately skipped oil changes. They used contaminated fuel. They tried systematically to break it. The Sherman kept running. Day after day, week after week, that American tank absorbed punishment that should have destroyed it. The engine, that supposedly crude radial design, ran smoothly hour after hour. The transmission, so simple compared to German designs, shifted cleanly under the worst conditions. The tracks, which looked flimsy compared to German track designs, proved nearly indestructible. And slowly, reluctantly, the engineers at Kummersdorf began to realize something unsettling. The Sherman was not poorly designed. It was differently designed. Every component had been engineered not for maximum performance, but for maximum reliability and ease of production. The welded armor which German engineers had scoffed at could be manufactured by semi-skilled workers in a fraction of the time required for cast armor. The simple transmission could be installed in minutes and repaired by any mechanic. The radial engine, borrowed from aircraft production, meant that America could leverage its massive aviation industry to produce tank engines. Nothing about the Sherman was perfect, but everything about it was practical.
One engineer at Kummersdorf, a man named Friedrich Bauer, kept meticulous notes during the testing. His reports, recovered after the war, reveal a growing sense of alarm. In early entries, he dismisses the Sherman as unsophisticated. By April 1943, his tone has changed. He writes about the tank's remarkable resistance to mechanical failure. He notes that the interior layout allows a crew to remove and replace the engine in under 4 hours, compared to over 20 hours for a Panther. He observes that the Sherman's gyro stabilizer, while not perfect, allows it to fire accurately while moving, something German tanks cannot do. And in one particularly striking passage, he writes that the Sherman represents a more dangerous threat than the Tiger because it can be everywhere. But Bauer's most important observation came during the disassembly phase. Every captured tank was eventually torn down completely. Every component was cataloged, measured, and analyzed. When the team removed the Sherman's transmission, they discovered something remarkable. The gears were not machined to the microscopic tolerances German engineers considered essential. They were rougher, simpler. By German standards, they were almost crude, and yet they worked perfectly. They were overbuilt, designed with enough tolerance that minor imperfections did not matter. This was engineering heresy to German sensibilities, but it was also engineering genius. The German approach to manufacturing demanded precision because their designs operated at the absolute edge of material capabilities. Every gear, every bearing, every component was optimized for performance. This meant that everything had to be perfect. A gear that was off by even a fraction of a millimeter could cause the entire transmission to fail. This required skilled machinists, expensive equipment, and enormous amounts of time. The American approach was different. American engineers designed components with enough tolerance that they did not require perfect manufacturing. A Sherman gear could be slightly imperfect, and the tank would still run. This meant that semi-skilled workers could produce components. It meant that production could be scaled up massively. It meant that America could outproduce Germany by orders of magnitude. The implications were staggering. Germany had bet everything on technical superiority. They had created the finest tanks, the finest aircraft, the finest weapons in the world, and they were losing the war because they could not build enough of them. America had bet on scale. They had created good enough weapons and built them in overwhelming numbers, and they were winning. The testing of War Daddy II continued through the summer of 1943. The engineers fired the tank's 75mm gun thousands of times, far beyond its expected service life. They wanted to see when it would fail. The gun kept firing. They examined the ammunition it used. American shells were simpler than German shells, easier to manufacture, less prone to defects. They were not as powerful as German anti-tank rounds, but they were reliable and plentiful. Again, that same philosophy: good enough, mass-produced, everywhere at once. They studied the electrical system. German tanks used complex electrical systems with multiple redundancies. The Sherman's electrical system was almost primitive by comparison. Single-wire ground return, simple circuits, but it rarely failed. And when it did fail, any crew could fix it with basic tools. The Tiger's electrical system required specialized training to maintain. The Sherman's could be understood by reading a manual. One of the most telling discoveries came when they examined the tank's welding construction. German engineers had been trained to create perfect welds: smooth, uniform, beautiful. The Sherman's welds were functional but rough. They looked hasty. But metallurgical analysis revealed that they were actually stronger than they needed to be. American welders had been trained to overweld rather than underweld. Better to use more material and more time on each weld than risk a weak joint. This was inefficient by German standards, but it meant that the failure rate on American tanks was incredibly low. And in a war of attrition, reliability mattered more than efficiency. The suspension system revealed another layer of American design philosophy. The Sherman used a vertical volute spring suspension. It was simple, consisting of easily manufactured springs and bogies. German engineers examined it with growing fascination. Their own tanks used torsion bar suspension, which was more sophisticated and provided better ride quality. But torsion bars required precise installation and were difficult to repair in the field. The Sherman suspension could be fixed with a wrench and replacement springs that any factory could produce. When they tested the Sherman over rough terrain, they found that while the ride was harsher than a German tank, the suspension absorbed punishment that would have destroyed more delicate systems. The track system presented another layer of American design philosophy. Sherman tracks were wider than German tracks, distributing weight more effectively over soft ground. But more importantly, they were constructed from relatively simple components that could be manufactured quickly and replaced easily. German track designs were more elegant, more efficient in terms of material usage, but they wore out faster and required specialized tools to repair. American tracks could be fixed with a sledgehammer and determination. In the field, under combat conditions, this mattered enormously. The team at Kummersdorf spent weeks examining the Sherman's armor protection. By German standards, the armor was inadequate. 76mm at the thickest point on the frontal hull. The Tiger had 120mm. The Panther had 80mm of sloped armor that was effectively much thicker. But the Sherman's armor was welded construction, which meant it could be assembled quickly by workers who didn't need the specialized skills required for cast armor. The welds were overbuilt, stronger than necessary, providing additional protection at the joints. The armor was also designed with the crew in mind. Hatches were large and positioned for quick escape. Vision ports were numerous. The interior was spacious enough that the crew could work efficiently. This focus on crew ergonomics puzzled the German engineers initially. Their tanks prioritized performance. Crew comfort was secondary. But as they studied the Sherman more carefully, they began to understand another aspect of American thinking. A comfortable crew was an effective crew. A crew that could escape quickly was a crew that would survive to fight in another tank. America was not just building tanks. They were thinking about the entire system of warfare, including the human element.
The more they tested WW2, the more the German engineers discovered a comprehensive design philosophy that extended to every aspect of the vehicle. The fuel system used gasoline, which was more available to American forces than diesel. The fuel tanks were positioned to minimize fire risk, and while Sherman tanks did catch fire when hit, the design attempted to give crews a fighting chance. The ammunition storage was a weak point, but later models addressed this. WW2 represented an earlier production variant, yet even this version showed careful thought about survivability. The fire control system on the Sherman included a gyro stabilizer that allowed the gun to remain relatively stable while the tank was moving. This was revolutionary. German tanks had to stop to fire accurately. The Sherman could shoot on the move. The stabilizer was not perfect. It works better at slow speeds than high speeds. But it gave American tanks a significant tactical advantage in mobile warfare. German engineers tested this system extensively, firing the gun while driving over rough ground. The results impressed them. The stabilizer did not guarantee accuracy, but it dramatically increased the probability of hitting a target compared to firing unstabilized. The radio equipment in the Sherman was another revelation. Every Sherman came equipped with a radio. Every single tank could communicate with every other tank and with command units. German practice was different. Only command tanks had radios. This meant that German tank platoons had to rely on visual signals or flags for coordination. American tanks could coordinate complex maneuvers through radio communication. They could call for artillery support. They could relay enemy positions. The tactical advantage was immense. And the radios themselves were simple, reliable, and easy to operate. Once again, that same pattern. Good enough, mass-produced, enabling capabilities that more sophisticated systems could not match. By August 1943, the German engineers at Kummersdorf had completed their initial analysis. Their report, classified as top secret, was sent to the Reich Ministry of Armaments. The conclusions were devastating. The Sherman, they wrote, was not a superior tank in terms of firepower or armor, but it was a superior design in terms of industrial warfare. It could be produced quickly, maintained easily, and operated by crews with minimal training. Most importantly, it represented an industrial capacity that Germany could not match. The report estimated that for every Panther Germany produced, America could produce 5 Shermans. For every Tiger, America could produce 10 Shermans. The report went further. It analyzed the strategic implications of American production capability. Germany's tank production was limited by skilled labor, by precision machinery, by material shortages. American production was limited primarily by the speed at which they could expand factory capacity, and they were expanding that capacity at an incredible rate. New factories were being built, existing factories were being converted. The automotive industry, the most advanced in the world, had turned its attention to military production. The numbers were staggering and getting worse. The report recommended immediate changes to German tank production, simplify designs, reduce manufacturing tolerances, focus on reliability over performance, standardize components, copy American production techniques, increase production of existing designs rather than constantly developing new models. The recommendations were detailed, specific, and practical. They were also, for the most part, ignored. Germany was too far down the path of technical complexity. The entire industrial system was built around precision manufacturing. Changing it would require time they did not have and resources they did not possess. And there was something else, something psychological. German engineering pride, the idea that quality mattered more than quantity, that perfection was worth pursuing even if it meant producing fewer tanks. This was not mere stubbornness. It was a fundamental difference in national character. German engineering tradition stretched back centuries. Craftsmanship was a cultural value. The guild system had emphasized mastery, the perfect execution of technique. Precision was prized above all else. The idea of deliberately building something to lower standards, even for practical reasons, felt like a betrayal of everything German engineers believed. It was not just about tanks, it was about identity, about what it meant to be a German engineer. The suggestion that they should copy American methods, should abandon precision for quantity, struck at the core of their professional pride. American engineering tradition was different. It came from a nation built on expansion, on making do, on solving problems with whatever materials were available. American engineers did not see simplified designs as inferior. They saw them as practical. Efficiency meant getting the job done, not creating the perfect tool. This mindset had been forged on the frontier, in the factories of the Industrial Revolution, in the pragmatic problem-solving culture of a young nation. And in a total war, practical beat perfect every single time. But there were individuals at Kummersdorf who understood. Friedrich Bauer was one of them. After completing the initial testing, he requested permission to conduct extended durability trials. He wanted to see just how far the Sherman could be pushed. Permission was granted, and over the following months, WW2 was subjected to the most brutal testing regime imaginable. The tank was driven for hundreds of hours without proper maintenance. Oil changes were skipped, filters were allowed to clog, the engine was run beyond its recommended temperature limits. The transmission was abused with harsh shifting and sudden reversals. The suspension was pounded over obstacles that no tank should traverse. The gun was fired until the barrels showed measurable wear. Everything that could be stressed was stressed to the breaking point and beyond. And still the Sherman ran. Components that should have failed kept functioning. The engine that should have seized continued running. The transmission that should have stripped its gears kept shifting. Bauer documented everything with increasing fascination. He was watching something that contradicted everything he had been taught about engineering. This tank should have died a dozen times. Instead, it kept running because every component had been designed with massive safety margins. The concept of design margins was not unknown to German engineers, but their margins were calculated precisely, optimized to provide adequate safety without wasting material or performance. American margins were different. They were generous to the point of seeming wasteful. A German gear might be designed to handle 10% more stress than expected. An American gear might be designed to handle 50% more stress. This meant the American gear used more material, was heavier, was less efficient, but it also meant it almost never failed under actual operating conditions. Bauer began to understand that this represented a completely different risk calculation. German engineers minimized risk through precision. Every component was manufactured to exact specifications, ensuring that the entire system operated within predicted parameters. American engineers minimized risk through redundancy and overbuilding. They assumed that components would be manufactured imperfectly, maintained imperfectly, operated under conditions far worse than ideal. So they built everything stronger than necessary. This approach had cascading benefits. Because components were overbuilt, they could tolerate poor maintenance. Because they could tolerate poor maintenance, tanks could keep fighting even when supply lines were stretched. Because tanks could keep fighting, America could sustain operations across vast distances. The reliability of the Sherman was not just a technical achievement, it was a strategic weapon. WW2 sat at Kummersdorf for the rest of the war. Occasionally, it was used for additional tests. Mostly, it sat in a warehouse, a silent testament to a truth that German leadership could not accept. Other captured Shermans arrived over time. Each one was tested. Each one confirmed what WW2 had revealed. The pattern was undeniable. American tanks were simpler, more reliable, and produced in quantities that made German production look like a cottage industry. But the real impact of WW2 was not on German wartime production. That was already a lost cause by late 1943. The real impact came after the war, when surviving German engineers had time to reflect on what they had learned. The lessons of WW2 became part of the collective memory of an entire generation of designers and technicians. Consider what happened in the ruins of post-war Germany. The nation was devastated. Its cities were rubble. Its industry was shattered. But its engineers survived. And those engineers had learned something profound during the war. They had learned that their traditional approach, while capable of creating magnificent machines, was not sufficient for the modern world. They needed to incorporate new thinking. The automotive industry that emerged in post-war Germany reflected this evolution. Companies like Volkswagen, Mercedes-Benz, and BMW had to rebuild from scratch. They had the opportunity to start fresh, to apply the lessons learned from years of analyzing Allied equipment. The result was a synthesis: German precision combined with American practicality. Vehicles that were well-engineered and reliable. Products that could be manufactured at scale but maintained high-quality standards. The Volkswagen Beetle became the symbol of this new approach. Designed originally in the late 1930s but not mass-produced until after the war, the Beetle embodied principles that would have been foreign to wartime German tank designers. It was simple. It was reliable. It was designed to be manufactured by the millions. It was not the fastest car, or the most powerful car, or the most luxurious car. It was good enough for millions of people, and it became one of the most successful vehicles in history, with production eventually exceeding 21 million units.
The Beetle's air-cooled engine was simple and robust. It could run under harsh conditions with minimal maintenance. The suspension was basic but effective. The body was easy to manufacture and repair. Everything about the Beetle reflected lessons that could have been learned from WW2. Simplicity, reliability, ease of production. These were American virtues grafted onto German engineering culture. The result was a vehicle that succeeded globally precisely because it did not pursue perfection. Mercedes-Benz took a different path, but arrived at similar conclusions. Their post-war vehicles maintained high-quality standards, but incorporated greater emphasis on reliability and ease of maintenance. The engineering philosophy shifted from creating the ultimate performance machine to creating vehicles that delivered excellent performance while remaining practical for everyday use. This was not a rejection of German engineering tradition. It was an evolution of that tradition, informed by hard lessons learned during the war. The industrial machinery sector showed similar evolution. German machine tools had always been the finest in the world. After the war, they remained among the finest, but the new generation of machines incorporated greater tolerance for variation, better maintenance accessibility, and simpler operation. The goal was no longer to create the perfect machine that required expert operation. The goal was to create excellent machines that could be operated by workers with reasonable training and maintained without specialized expertise. This shift in philosophy was subtle but profound. It represented a change in how German engineers thought about their work. Perfection remained an ideal, but it was tempered by practical considerations. Reliability became as important as performance. Ease of manufacture became a design criterion rather than an afterthought. These changes did not happen overnight. They evolved over decades, but they were rooted in experiences like the testing of WW2, in the realization that American engineering had something valuable to teach. The engineers who tested WW2 lived with a strange knowledge. They had been proven right and wrong simultaneously. Right that German tanks were technically superior in direct combat. Wrong that technical superiority was what mattered most. Some of them wrote memoirs after the war. Some gave interviews to historians. Many simply went back to work, designing new machines for a new era. But in their minds, in their understanding of what engineering meant, something had fundamentally changed. There is a broader lesson here, one that extends beyond tanks and beyond World War II. It is about the nature of complex systems, about the difference between optimization and robustness. A highly optimized system performs brilliantly under ideal conditions, but it is fragile. When conditions change, when something goes wrong, when the unexpected happens, the entire system can collapse. A robust system performs adequately under ideal conditions, but it keeps functioning when things go wrong. And in the real world, things always go wrong. This principle manifests in countless ways throughout modern civilization. Consider financial systems. The complex derivatives and interconnected instruments that seemed brilliant in the early 2000s collapsed catastrophically in 2008 because they were optimized for specific conditions and had no tolerance for deviation. They were tiger tanks, magnificent in perfect conditions, disasters when reality intervened. Contrast this with simpler, more conservative banking practices that provide lower returns but survive economic shocks. These are Sherman tanks, not optimal, but robust.
Consider software development. The push for efficiency has led to incredibly complex systems with multiple dependencies and minimal redundancy. When a single component fails, cascading failures can bring down entire networks. Modern internet infrastructure is powerful but fragile. It has been optimized for performance at the expense of robustness. Older systems with more redundancy and simpler architecture were less efficient but more reliable. The trade-off between optimization and reliability is the same trade-off German engineers confronted when testing WW2. Consider supply chain management. Modern just-in-time manufacturing eliminates warehouses and inventory, maximizing efficiency. But it also eliminates buffers. When the unexpected occurs, when a pandemic shuts down factories or a ship blocks the Suez Canal, the entire system freezes. There are no reserves, no margins, no tolerance for disruption. This is optimization without robustness. Older supply chains maintained larger inventories, which seemed wasteful in good times, but provided resilience during disruptions. The Sherman tank's design philosophy, with its generous margins and overbuilt components, reflected the same understanding. Better to carry extra capacity and waste some efficiency than to operate at the edge and risk total failure. The military applications of this lesson extend far beyond World War II. Modern weapons procurement often falls into the same trap that consumed German tank development. The pursuit of cutting-edge technology, of maximum performance, of technical superiority. Each new weapons system becomes more complex, more expensive, more difficult to maintain. Development timelines stretch to decades. Costs spiral into billions. And the result is often a small number of highly sophisticated weapons that perform brilliantly in ideal conditions, but prove difficult to deploy and maintain in actual combat. The F-35 fighter jet program exemplifies this challenge. The aircraft is technically remarkable, incorporating stealth technology and advanced avionics. It is also the most expensive weapons program in history, with development costs exceeding $1 trillion. Each aircraft requires extensive maintenance. The supply chain for spare parts is complex and frequently disrupted. Combat readiness rates are often below 50%. This is a Tiger tank, magnificent in its capabilities, challenging in its practical application. Contrast this with older, simpler aircraft like the A-10 Thunderbolt. The A-10 is not stealthy, it is not fast, it is not particularly sophisticated, but it is reliable, maintainable, and effective at its design mission of close air support. The airframe is durable enough to absorb significant damage and return to base. The gun is simple and powerful. The aircraft can operate from rough airfields with minimal ground support. This is a Sherman tank. Not optimal by modern standards, but practical and effective.
The same pattern repeats across military equipment. Special operations forces often prefer older, proven weapons over newer, more sophisticated alternatives because reliability matters more in combat than performance specifications. The AK-47 rifle, designed with loose tolerances and simple mechanics, has remained in service for over 70 years because it functions under any conditions. More sophisticated rifles may be more accurate, but they require more maintenance and are more sensitive to dirt and damage. The choice between optimization and robustness remains relevant. Understanding this trade-off requires a shift in how we think about engineering and design. We are culturally predisposed to admire optimization, to celebrate efficiency, to pursue the best possible performance. These are valuable goals, but they must be balanced against the need for reliability, for tolerance of imperfection, for operation under real-world conditions. The German engineers at Kummersdorf learned this lesson through bitter experience. They had created the best tanks in the world by traditional metrics, and they lost the war because best was not what mattered. WW2 forced them to confront uncomfortable truth, that their technical sophistication was a strategic weakness, that their pursuit of perfection had created fragility, that their American adversaries, whom they had dismissed as crude and unsophisticated, had actually understood something fundamental that they had missed.
The Americans had not set out to build the best tank. They had set out to build the right tank for industrial warfare. And they had succeeded brilliantly. The story of War Daddy 2 reminds us that context matters more than absolute performance. A tank that is invincible in direct combat but breaks down constantly is less useful than a tank that loses direct combats but remains operational. A system that performs at 100% efficiency under ideal conditions is less valuable than a system that performs at 80% efficiency under all conditions. A solution that is perfect but rare is less impactful than a solution that is good enough but ubiquitous. These principles apply everywhere. In infrastructure design, where the temptation is to optimize for cost and efficiency at the expense of redundancy and resilience. In software architecture, where the push for performance leads to complex systems that are difficult to maintain and debug. In organizational design, where efficiency initiatives eliminate slack and buffers that allow organizations to handle unexpected challenges. In personal life, where the pursuit of optimization can create fragile routines that collapse under stress. The alternative is to embrace robustness as a primary design criterion, to deliberately include margins and buffers, to accept that the optimal solution is often not the best solution, to recognize that reliability, maintainability, and resilience are features worth paying for even if they reduce raw performance. This requires humility. It requires accepting that your creation will not be the absolute best by every metric, but it also creates systems that actually work in the messy, unpredictable reality of the world. War Daddy 2 embodied this philosophy. It was not the best tank on the battlefield. German tanks outgunned it, German tanks had better armor. In a one-on-one duel, a Tiger would win almost every time. But War Daddy 2 represented something more important than combat prowess. It represented a system designed for war rather than for battle, designed for operations across continents rather than for perfect performance under test conditions, designed for crews with basic training rather than for experts and factory precision. And in the end, that is what won the war. Not superior technology, not better tanks, but more tanks. Tanks that kept running, tanks that could be repaired in the field, tanks that could be operated by conscripts with a few weeks of training. Tanks that embodied the industrial might of a nation that understood scale better than any nation in history. The Germans created masterpieces. The Americans created a system. And the system won. The final irony is that War Daddy 2 taught these lessons to the very people who were trying to defeat America. The German engineers at Kummersdorf were looking for weaknesses. They were trying to understand how to beat the Sherman in combat. Instead, they discovered that the Sherman represented a completely different understanding of warfare, an understanding that made tactical victories irrelevant if you could not sustain operations, an understanding that reliability was more important than performance, an understanding that won wars. And so, War Daddy 2 sits in the imagination of history, a symbol of a truth that every generation must relearn, that the goal is not to be the best, the goal is to be effective. That perfection is often the enemy of good enough, that the things which matter most are rarely the things we celebrate, that behind every glorious victory are thousands of unglamorous machines doing unglamorous work reliably, day after day, battle after battle. Remember War Daddy 2 when you see the next breakthrough technology announced with great fanfare. Ask yourself whether it is optimized or robust, whether it will work under real conditions or only under ideal conditions, whether it can be maintained and repaired, or whether it requires experts and perfect parts. Remember War Daddy 2 when you design your own systems, your own solutions, your own approach to problems. Ask yourself whether you are building a Tiger or building a Sherman. The world needs both, perhaps. We need people pushing boundaries, creating the best possible versions of things, exploring the limits of what is possible. But we also need people building reliable systems, creating practical solutions, ensuring that things keep working when conditions are terrible. And if history is any guide, the latter matters more than the former. The Sherman tanks won World War II. The Tiger tanks are in museums. That should tell us something about what actually matters in the long run. Reliability, practicality, good enough. These are not exciting words, but they are the words that describe victory. They are the legacy of War Daddy 2.